So I'm going to be talking about powering TensorFlow with big data. I'm going to be looking at a wonderful collection of different tools that historically do not play nicely together, and make them sort of play nicely together for the length of one demo. I'm Holden Karau. You can follow me on Twitter. I like cats. Yeah, so my name is Holden. I'm a developer advocate at Google. My preferred pronouns are she or her. It's tattooed on my wrist, which is really useful when I'm super jet lagged. I'm just like, where am I and who am I? So no worries. I am Apache Spark PMC, which is kind of, well, actually this is OSCON, but anyways, I like to think of it as the best kind of tenure that I could ever get, which is they can't really kick me out, but they don't have to pay me. So it's not a very useful tenure, but it's still cool. And I also contribute to Beam. And so the things I'm talking about today, I'm at least somewhat invested in. So I may have a combination of a rosier and a less rosy picture by virtue of working on them. I learn a lot of their faults. I've worked at a whole bunch of other companies. They all paid me money and were excellent people when they were paying me money. I'm a co-author of 2 books. You can buy them with money. High Performance Spark is almost completely unrelated to this talk, but I got a much better royalty deal on that one, and so I think that book is amazing. You can follow me on Twitter. Slides will go on SlideShare. If you're interested in seeing code reviews for a project with 500 open pull requests that just somehow seems to never go down, you can follow my code review live streams, and I have a bunch of Spark Talk videos as well. In addition to who I am professionally, I'm trans, queer, Canadian, and part of the leather community. And I'm here on a work visa. It's a really lovely time to be in America on an H-1B. It's just so exciting. Every day I wake up and I'm like, I still have a visa, great. Anyways, but I think this is not directly related to machine learning, but I think it's useful for those of us that are going to be doing this stuff to remember if we're all just from the same background, we're just going to build the same crappy shit that we already have, and we're just going to just make it reinforce all of our existing stereotypes, and that's going to suck. And so you should try and like be inclusive of other people and be awesome instead of mean on the internet. Okay, so I'm hoping you're nice people. You've laughed at some of my corny jokes, but not all, so that's fine. If you mind pictures of cats, there are other talks happening at the same time. There is no shame in leaving. I'm really curious, how many people here are familiar with TensorFlow? That is way higher than I thought. That's awesome. Okay, how many people are familiar with Beam? That is also higher than I thought. Flink. Okay, and Spark? Okay. Is anyone not familiar with any of these technologies? Awesome, yay! Hopefully I can trick you into learning one of them, or all of them. I want to be clear, we're going to do a demo, and hopefully the demo will not crash, but this is not the kind of demo where you should go and try and recreate that in production. That will go poorly. And by poorly, I mean, if you're lucky, it will crash, and if you're unlucky, it will produce incorrect results. So be careful, and yeah. I'm going to show 2 different ways of doing TensorFlow on big data. I'm going to show one that uses Beam and one that uses Spark. And it'll be fun, and hopefully both demos will run. But if not, we have 2, so one of them will probably run. It's pretty good odds. Okay, yeah, so just really, really seriously, don't use this stuff in production today. It's like, I do not want to be the lady that's in the like engineering textbook in 20 years who was killed by her own software project. Like, no, okay? Because that is not what I want my legacy to be. I want it to be like cute stuffed animals and shit. Anyways, and these are not things that you should never do in production. If they were, I wouldn't be talking to you about it. Or I would, but I'd be drunk. But this will get better. So there's why there's a date in there. I hope it's actually today's date. But this will get better just for the people on the recording. This may actually already work. For those of you here today, give it a few months. Okay, so I'm going to talk about why this is kind of hard, why it matters to TensorFlow. I'll talk about why everything else sucks too, because the last time I gave a talk like this, people came up to me afterwards and were like, wow, that sounds really bad. What should I do instead? And the answer is nothing. We're fucked. Okay. And yeah, we'll do a TF transform demo with Beam on top of Flink, and we'll maybe get to experience a system crash together. And then we can have a mid-session Q&A while I reboot. Keeps it exciting. Okay, so why do we need to power deep learning with big data, besides more buzzwords on that bingo game that we play? So part of it is, if you have megabytes or kilobytes of data, deep learning is probably not for you. You probably want pandas and scikit-learn and training a nice linear regression model, right? You just don't have enough data. Admittedly, that being said, if you're trying to raise venture capital in San Francisco, I understand that you're going to use deep learning regardless of whether or not it's the right fit. So that's all right. And one of the things that I think is important to remember is we always have to do some feature prep. Even if you're training on mnist.csv, you have to do some feature prep. And even the Chicago taxi data, all of these things require some pre-processing. If it doesn't, you're probably doing like a Kaggle competition, and that's cool, but that's probably not going to be your real production workloads. So TensorFlow on its own, in the very core part, doesn't have a lot of happy tools for us to do our feature prep. There's a whole bunch of really cool things in the ecosystem, like TF transform, which we can use. And TF serving pairs nicely with TF transform, because one of the great things about doing feature prep is you often get to write your code twice, sometimes in 2 different languages. And that results in like 0 bugs whatsoever. Translating my code between Python and Java is totally a reasonable production strategy. So instead, though, we can use TF transform, which integrates into our serving pipeline, and we can not have piles of custom code where I copy and paste it and then change camel cases to underscores or vice versa. Okay, so if you're old school, your feature prep is a custom job in your favorite big data tool. Mine is Spark, sorry. But yours can be something else, that's totally fine. You run it, you train on your prepared data, and then you rewrite your feature prep code to run at serving time, and you just don't fuck it up, which we're all really good at. And so just make no mistakes in your code, and you'll be fine. Alternatively, you are like, wow, you know what sounds fun? Not taking the mean of a bunch of things by hand. And binning a whole bunch of strings really isn't the business logic that I'm trying to express here. It's not my differentiator. And so we can use a pre-packaged happy transform system for us. And it's awesome. It integrates into serving time. It's open source. It's written in Python. And it runs on top of Apache Beam. Especially if you are a Google Cloud customer. And if you are, thank you for giving my employer money and paying my salary. If you're not, that's all right. But if you're not, you're going to have a lot of bugs. But it's OK. The bugs will get fixed, and it'll start working. And so actually, I probably should have clarified. You can totally use this stuff in production today on top of Google Cloud. And so if you happen to be one of the fine people who pays my employer for services, go and enjoy our high-quality services. They are excellent. This will work in open source better soon. So what does our fancy pre-processing look like? We have our pre-processing inputs. We center some things. We scale some things. And we turn some strings into integers. Very exciting. We have 1, 2, 3 features. Totally reasonable to use deep learning on 3 features. Yeah. OK, so what does this look like? This slide is clearly stolen from someone else because there is no cat picture. And so we specify the analyzers, and then the analyzers are going to come together with some data, and they're going to analyze. And then we get constant tensors that we use at serving time. And so it computes the mean, the standard deviation, and it does all of our bucketization and all this cool stuff. And this is nice because we don't have to rewrite our code, and I also don't have to write a bunch of shit to do distributed quantile computation, which is surprisingly annoying. I spent 3 weeks doing that once. It was not fun. And so there's a whole bunch of things that are built into it. It's cool. And you can go find some more things in the TF transform documentation. And so let's say that we actually want to take this and we want to use it on real data. So TF transform is written with Beam for its processing, and it doesn't work super great yet, but we can make it work for the purpose of a demo. And if you want to come and help us fix it, it's open source. Patches welcome. OK, that went over about as well as expected. So what does this look like? We have a whole bunch of stuff in master. It's not released, and it crashes. We have this cool portability framework, which is an excellent approach to recreating all of the old problems we had, but this time with containers, which actually is really useful for things like TensorFlow, where I have sort of dependency hell quite easily. And so the containers actually do bring us happy things besides just another layer of abstraction and opportunity to write a promo packet. We have a hacked up Python SDK that sort of works with this, and we have a Go SDK as well. You can't do any of the deep learning stuff in Go, but are there any Go users here? If you want to come find me later, I have a Go word count demo for you that is super exciting. I promise. OK, and then there's a bunch of weird things about permissions to just make your data world writable. It's fine. OK, so what does this architecture diagram look like today? We have Python that kind of talks to Beam, Go, which kind of talks to Beam, and then Java, I mean, it actually talks to Beam, but it doesn't really use the portability layer, so that's why it's ish. And then Beam can totally run on top of Google Cloud with its portability layer. It's fancy, you pay money, you receive services. And the other option is it can kind of run on top of Flink. And so then you don't have to pay money, or I mean, you probably do, but to someone else. And that's OK, right? And this high quality design, we have our driver sort of program. And we can see that we have Python and Java together, and then we have Python Beam goes into Java Beam, goes into Apache Flink, and then on the workers, we have a lot of RPC calls and then copying data around. And if you look at this architecture diagram and you're like, this looks kind of slow, you are correct. But we're getting better. There's some really cool things that I'm going to talk about in the end about how our data transfer can get a little faster. And so this is all well and good, but this is talking about running Python on top of a distributed system. And that's what we need, though, to use TF transform. That's why this stuff all matters. There's a whole bunch of things which are coming soon, and they're not super working, but we can hack them up by editing Docker files to install all of our dependencies. And it's nice. And so we have the Chicago taxi data sample set because it's nice and small and it fits on my laptop. And we're going to go ahead and train a TF transform model with that. And so this one does string to integers. It does some bucketization. It does a bunch of other things for the different type of features. And I'm going to, everyone please stop watching Netflix. We're gonna start our Beam runner. And so our Beam runner, there's a Flink one, and there's a Spark one, but the Flink runner supports the portable architecture, so we can run Python on it, and we can also run Go on it. And so that's why it's the one we're going to use today. And then I'm going to go over into this model analysis repo. Oh, and you can see my git commits like hack. OK, ignore the branch name. Everything is fine. OK. Those are my exports. So I have a bucket, which I'm going to use to store my stuff in. I have some credentials, which, due to a weird bug, we actually have to copy in 2 places. And I have a very fancy script called preprocess_flink.sh. We're going to run it, and it might not crash. Yeah? OK, cool. Let's go for this. And I am OK. Well, that one I can fix. OK. Okay. We're gonna, okay, cool, awesome. Okay, cool. So it looks like I forgot to include my virtual environment. I could have sworn I did this like 5 minutes ago. Okay, I don't know why I deactivated my virtual environment. Okay, so the first thing this does is generate some job ID stuff. It's just to make sure that we don't step on someone else's files. Caches the input data because the input data is already stored in GS, and I didn't want to risk it too much with the Wi-Fi. Felt like reusing that would probably be kind of useful. And then it comes down here and it kicks off our fancy Python preprocess script, which is the one which looks like this with a whole bunch of like boilerplate up at the top. And so it's going to go ahead and it's going to build this tar file of all of the things that it requires. The first bit that it did was all running locally. So all of these parts were actually just local. It's setting up. And then it's going to go over here. Ooh, ignore that thing that said memory leak. And so this is the part where now our job server is receiving requests, and it's starting to actually kick off jobs on Flink for us. And this is cool. Oh, I can make the text bigger. Yeah, and so it's actually working. I should sound less surprised. It's working, which I totally expected, for sure. And based on the last time I ran this, this takes either 2 minutes or never finishes. Executing time is 2 minutes and 58 seconds. Oh, crap. Well, 2 minutes on the other side over here. Oh, yay. Actually, it finished faster, 1 minute and 20 seconds. Yay. The demo didn't crash. OK, thank you. Thank you. The last time I had something like that, it was the word count demo, and no, there was no clapping. OK, and the shell script actually repeatedly runs the demo in a loop, just in case it crashed. And so it's going to go run the demo again, but that's OK. I can scroll up here to the part before, and we can see a lot of warnings. It's not very happy about us, but it output its models, and it did happy things. So that worked, and now it's going to run again. But I'm not going to watch it the second time because it's probably not going to work. So 50% success rate is pretty good on data that fits on my laptop. Oh dear. OK. Yay, it worked. And if you want to go see this demo code, it is a fork of something, of a demo. And it's got a whole bunch of stuff sort of pared down so we don't cross any of the places where we've had exciting features occur that are currently undocumented. And so don't use this in production, but you can go and run this demo again on your laptop. And I would recommend putting it in a shell script, which tries it repeatedly until it works. And you, too, can have the experience of having a trained TF transform thing. And in the future, for the people that know Spark, Beam, beyond the JVM, in theory, will kind of work on Spark as well. I should have probably taken out the issues for the future. But maybe I was just pessimistic. So in the future, more of the runners will support the portability framework, and we can run arbitrary code across all of them. And it'll be amazing, and you won't have to install Flink or whatever. OK, so now what? We've trained a model. Well, we haven't really trained a useful model. We've trained a feature preprocessing model. And so what do? We can use TFMA. Which can serve this directly. And we can also now jump back into the existing guides from the wonderful TensorFlow people and just not have to do any crazy stuff. Like the existing guides now all work. You don't have to use this fork of a fork of a fork. You can just follow along the normal stuff. But you're not going to run this in production for reals, because it'll probably crash if you try and do that. OK, who wants to see word count? Oh, crap. OK, wish me luck. Let's do a git clear so you don't see any of that. This is probably only recorded. SDKs, go, build, bin, oh no. No. Word count. Oh, maybe minimal word count sounds more likely to succeed today. Oh, it's not compiled. Oh, damn it. I may have actually forgotten to compile this demo because I did a clean build right beforehand. Sorry. Okay, the word count demo works probably, and we can rebuild it and we can do it at the end if there's time. So I'm gonna go ahead and swap this Python to Go, and it'll build my Go dependencies for me while we finish the talk, and we can do a Go word count demo later. It'll probably compile. Okay. Yeah. Okay. We'll come back to the Go word count, and we'll look at Spark because there were people who liked using Spark. So what can we do in other systems? And the spoiler is that it's not much better. And everyone takes different trade-offs, but all trade-offs here have been kind of rough. Oh, okay. Yeah, my slides are running super fast because I'm running Gradle at the same time. So PySpark, which is what we would have to do to be able to really use TensorFlow and Spark, depends on pickling, sockets, pipes, and JSON. And I do not have a funny image for JSON because JSON is not funny, but at least JSON is not XML. So there's that. That being said, we do use XML, so that's great. Okay, cool. Happiness is overrated. So PySpark is the Python interface to Spark. It's the same general technique that's used in the other non-JVM languages for Spark. And it's how we can run similar feature prep and actual TensorFlow jobs with Spark. It has some serious performance hurdles from our core design, which we have not yet fixed, but totally are probably trying to this year. It looks good. And I have a benchmark, which is a lie, but it says it's 200 times faster. So that's pretty much the same thing as success, right? So, okay, if you remember our previous architecture diagram, this may look kind of familiar. The only difference is we don't have containers, so dependency management sucks, especially when you're running dual Java Python jobs at the same time. This is kind of rough. Just have the right version of TensorFlow installed on every node in your cluster. Good luck. And excitingly, I know I throw a lot of shade about Spark, but Flink looked at that architecture diagram and said, you know what? That sounds slow, and I'm going to do that. But instead of sockets, I'm going to use memory-mapped files. And this resulted in about a 0% performance difference, but has some exciting possibilities for the future. And so, okay, this is the TLDR. Everything sucks. This is kind of slow, and the error messages make no sense. Has anyone gotten a PySpark error message that was easy to understand? What? You have? I'm impressed. No. Oh, you're, God damn it. OK. So 0 people here. And so I like throwing this out just when I'm talking to people. Don't feel bad that the Spark error messages make no sense. When I read them, I am still confused. And I've been working on this for 5 years. And there's other issues, but they're not as important. So let's move from the Chicago taxi example to MNist. OK. No one likes MNist, apparently. And everyone really loves taxis in Chicago. So there's this project called TensorFlow on Spark. It's pretty simple to use. It's, you know, we have this nice thing. It's not so bad. The only problem is it's really slow. And that's unfortunate. And We can fix this, though, by making the interchange format not pickles and JSON with a little bit of XML for flavor. So instead, we're going to use something else. And so what we're going to do is we're going to use Apache Arrow. And your data can be copied as fast as this cat transitions universes. OK, yeah. And here's a vendor benchmark from a vendor which I no longer work for. That implies your jobs will be 242 times faster. This is not true, but it sounds good. And it turns out that your jobs can be probably a lot faster. You're probably still not going to get a 3x speed up. You could maybe get a 2x speed up. For TensorFlow related stuff, it's probably not going to be quite as big. It's probably going to be a 25-ish% speed up. But definitely do your own benchmarks and don't trust people like me who try and sell you things. And so we have this diagram. And the thing in the middle is Arrow, and we see Java can talk to Arrow, which is useful because all of our big data stuff is in Java. Arrow can also directly read Parquet files. So if anyone's just like, you know what I really don't want in my life ever again is a Java stack trace around a seg fault. You can replace that with a Python stack trace around a seg fault. And then it supports a bunch of backends. Today it's R and Python and even CUDA, and other things are coming soon. And we can rewrite our code fairly simply. Spark, when we're writing Python code, this is how we add two numbers together, very advanced. We can see definitely that we want to do this in Python because it's numeric computation. And Java and adding integers, I don't know, right? And so we rewrite it here, and now we have a UDF to add two integers. But we can actually do this inside of TensorFlow on Spark and make it go faster, if you believe benchmarks, much faster. And so this is sort of the core workpiece logic of TensorFlow on Spark. It has this RDD that represents all of the sort of training batches that it needs to go through. And then it uses this thing called for each partition, which essentially says, do some work on this data, but I don't care what comes back, just do the work. And this will transform into something magical, aka fast, but unreliable. And so what we do is we replace that for each with this pandas UDF, where we return a bunch of zeros because there's a bug where you return nulls. So we did bang up job there. So we just return a bunch of zeros, and then we call for each on it at the very bottom. And this is cool. It makes our job faster. And this looks like Java goes to Arrow, goes to Python, goes to TensorFlow. But still has a lot of steps, yeah? But it turns out that just by replacing pickling with Arrow, we can get a lot better performance. And this is fun and nice and happy. And in theory, we could do other things to make it faster. We could try and use memory-mapped Arrow. The Flink people were on to a good idea. It just turns out memory-mapped pickled files were useless. But memory-mapped Arrow could totally be kind of cool. There are other things we could do, but I'm unlikely to do them because I'm lazy. OK. Here's a whole bunch of references. If you're interested in not running this in production, but playing around with it when you're prototyping, you can click on all of these links, including the one on the bottom, which you cannot see. I will upload these to SlideShare, and you can play around with it there. If you want to come join me in different places, here's some things. I guess we unfortunately have enough time to go back and see if that demo is finished. Compiling. Oh, OK. It compiled. OK. Let's see. I really hope this works. OK. SDKs, go, examples. OK, yeah. Oh, wait, did it not? Damn it. The Gradle target changed and it didn't compile anything, but it fetched a whole bunch of things from CoreOS instead. Yeah, I'm not going to have the word count demo work. I'm sorry. I know your hearts were all set on word count. I feel really bad about the word count demo not working. Yeah, let's just do questions instead of having me try and fix a word count demo live. I think that's gonna be more fun, at least for me. I'm sorry about word count.
Here you go. If you have any questions, I can come around the microphone.
So I don't know if I want to really know, but why do you need Gradle in a Go program?
Yeah, we use Gradle to fetch a whole bunch of dependencies and put them in magical places, and then we call go build, and then it builds sometimes, except not today apparently. So that's cool. I don't know. Maybe Gris remembers how to build the Go examples. No. Okay. Never mind then. Sorry.
If you can put your hand up, I can come around the microphone.
Boo is also available for questions. Her experience is mostly barking at computers to make them go faster. Oh, okay, so the question is, does barking at computers make them go faster? And the answer is 100% of the time that my benchmarks are correct. Okay, so there are no questions, but if anyone is really, their heart was set on the Go word count demo, come find me outside, I'll fix it, and you can count some words with me. It'll be really fun. Thank you all for coming.